Hello everyone, welcome to this CAM Robotics session. Today I will talk about the CAM functionalities for robot programming. I will start showing a few slides and then I will jump to CAM software. In the first slide we can see robotic processing applications. For example, we have engraving, wood milling, deburring, and all these examples shows a subtractive manufacturing. But we can use CAM and robots for additive manufacturing also, like welding and some other process. Here we can see some robotics challenges. For example, an accurate toolpath, continuous changes, and also external device synchronization. Doing a manual programming, it's hard to accomplish all these challenges. But using CAM software for robot programming, we can accomplish all these challenges easily and quickly. So let's talk about the CAM Robotics product highlights. Using CAM for robotics programming, we can easily and faster create 3D and complex toolpaths. So we can also plan, validate, and optimize the process. And using the CAM post-processors, we can output robot code, and also we can develop and customize those post-processors if needed. Here we can see some other highlights. On CAM Robotics, we can use the common CAM interface. So in this case, we will have a short learning curve. We can also have 100% associativity when product changes. If there is any product change, we can quickly see those changes and also update the paths and the process, and we can easily replace robots if needed. If we start the programming process using one specific robot and during the programming process we have to change the robot, we can do that following a few steps. And here in the next slide we have some customer benefits. We can easily provide production-ready output. We can validate programs graphically for faster setups. We can also quickly create complex motions, programs, and process. And using CAM, we can streamline the programming with process automation at all levels. So let's jump to CAM and see how it works. Here I have the first example. So in this example, we have a cooker robot and we have a milling spindle in this robot. Also, we have this part as a part we will create some paths. Let me hide the cell face, and here, as we can see, we have a clean structure where we have the part geometry defined, we have blank geometry defined, and also here we have some tools already created. So we have a milling tool, we have a ball mill in this case, and I will start creating an adaptive milling path to rough this outside profile of the part. So I will use this tool. So let's insert an operation. Let's use adaptive milling, program group, workpiece, and OK. In this case, I will change the tool axis and I will define the tool axis normal to the top face. After that, I will change the cut levels, so I will select the last cut level as the bottom face, and as I would like to create the path just outside, I will specify a trim boundaries to limit the tool path. Okay. So let's here, oops, and here. Okay, and let's create the path. So as we can see, easily and faster we have a roughing path using an adaptive milling operation. So after we create the adaptive milling operation, we can also run the verify toolpath. So here we can see the tool. Let's change to real tool. And if we would like, we can see also the material removal. So let's verify toolpath and let's hit play. On verify also we can switch to assembly and see the real 3D cutter. Okay. After we verify the toolpath, we can check the robot behavior using the robot simulation. So in this case, I will go to next step, and as we can see, we have some warnings because we have the robot in a completely wrong orientation and position. This can't be done using the robot this way. So to fix that, we have in an XCAM the robot control. So in this case, we will have the ability to control all robot configuration, including the external axis and device. So the first thing I would like to do here, for example, is rotate the external axis. So I will change it to -90 degrees, and this is the position I would like to use the external axis. So in this case, I will go to Positioner tab and I will select Constant Joint Value and Inherit from the graphics. And I will select OK. And now I will apply and validate the rule. Okay, so let's check the robot behavior again. And as we can see, we still having a positioning problem with the robot. So in this case, we can also go back to robot control, and we have an option called path position. So I will select the path position here, and now I can see the correct robot orientation. So in this case, I will use the configuration tab and I will inherit the robot configuration. So I will select apply, and I will apply the rules and validate the rules again. Okay, and now we will have a good process working. So no more warnings, and as we can see, we have the robot at the correct orientation. So we can also see the material removal, and in this case I will hit play. Okay, let's stop and reset. One other important thing here is that we know the robot will not jump directly from this position to the start point. So in this case, we have to configure the home position, and then we can see the motion from the home position to the start point. So in this case, I will go back to robot control, and I will add in the poses here a home position. So before start operation, I will add a new pose, and I will call home position. And also I can easily copy and paste the home position. I will apply and OK, and I will apply and validate the new rules. And then we can see the new robot behavior. Okay, so let's start robot simulation. So now we can see the robot will start from the home position here and will move to the beginning of the path. So now we can see the approach motion, how it will work. And also we can check if it will working okay for our process. So let me hit play and increase the simulation speed. Okay, and we will see the same at the end of the path. When the path finishes, so the robot will go back to the home position. But now let's create a variable 2-axis toolpath. So in this case, I will use the ball mill, and I will create a variable guiding curve operation. Okay, I will select this face as a cut area, and I will select this curve as a drive curve. I would like to cut on the left side, zigzag, away from curve, 1 millimeter step over, and 10 paces. It's okay. And let me use the 2-axis as normal to drive and generate the path. Okay, that's perfect. Now we can see the variable two-axis toolpath. And now we need to check the robot behavior on variable two-axis path. So let's check the first positioning, and again we do not have the correct robot orientation. So in this case, let's work with the robot control. I will add the home position and copy and paste, apply, and I will select the path here, and we have the robot in the correct configuration. So the robot configuration, I would like to inherit the current configuration, and in this case I will select OK and run, apply and validate the rules. Okay, so now let's check the robot simulation. Okay, so let's move to the first position and then check the robot motion. So that's perfect. As we can see, the tool is perpendicular to the part face all the time. But now we are using just the positioner axis as a fixed position. But I would like to rotate and synchronize the positioner axis, the external axis. So in this case, I will go back to the robot control and I will select some point in the path, and for example would like to keep this two-axis orientation. So in this case, in the positioner, I will change to two-axis constant and I will inherit the two-axis. So I will select OK here and again apply and validate the rules. Now when we run the robot simulation, we will see, let's change the speed, we will see the external axis moving, and now the external axis is synchronized with the robot. And as we mentioned it before, we can do that easily and quickly. Okay. Also, during the robot simulation, we can check collisions. So we can check tool and IPW collision. So collision between tool and IPW. We can also check collision between tool and part and in between the robot and cell components. So for example, we can turn on the machine collisions And for example, we can select a component. In this case, I will select the robot spindle, and I would like to check a collision between the external device table. So now I can define a clearance, for example 10 millimeters, and now when I run the machine, the robot simulation, the system will check a collision between the spindle and the table, and if there is any collision, the system will pop up a message. So I will have to find a solution for that collision. Now I would like to talk about some other examples. So here I have one other example, and in this case we have a different scenario because we have a part attached to the robot. So in this case we have the burring, polishing and lineage process, and as we can see, the way to create the burring process, for example, is exactly the same as we use it to create the adaptive milling path in the previous part. So here we have the deburring process. Also for lineage, in this case we used a curve point variable 2-axis operation, and also it's the same way we used in the previous part. So as we can see, we have here the desired path. So now let's run the robot simulation and see how it works. So let's start the robot simulation. Okay, and let's hit play. Polishing and linishing. Perfect. So after the process, the robot go to the end position to leave the part, to left the part there. And also one other example I would like to show is the welding process. So in this case, I have a welding part here, and I have a welding path, and also I used the variable 2-axis operation to create the welding path, so we can verify the path and we can see how it will work. Okay, so now let's run the robot simulation and check how the robot behaves. Let's hit play here. Okay, and play. Perfect. So these are some of CAM functionalities for robot programming. I hope this help you to understand how easily is to create a robot process using CAM Robotics. Thanks for watching and see you in the next section.